Hey, I think you know how to express Archimedes' principle mathematically. We say the buoyant force is equal to the weight of fluid displaced, but the weight of a fluid is the mass of the fluid multiplied by gravity, but then again the mass of a fluid is the density of the fluid times the volume of the fluid, and then we still have to throw in the expression g. So there we go. We can express the idea that an object that's either partially or completely submerged has a buoyant force that's equal to the density of the fluid that's being displaced times the volume of fluid displaced times g. Now here's an object that's fully submerged, not partially submerged. The object I'm speaking of is the hot air balloon, and a hot air balloon is fully submerged within the atmosphere. So if the balloon weren't here, then what would take its place? Well, in place of the balloon would be a parcel of air. It's relatively colder, that takes up the exact same volume. So if we make a free body diagram, we show two vectors. One vector pointing down, well, that's the weight of the hot air balloon, and then the other vector pointing up, that's buoyant force. Now, I don't think anything's going to change the buoyant force in the control of a hot air balloon. The canopy, the material, the fabric that's filled with the hot air, doesn't really expand or collapse much, so its volume stays the same, and if buoyant force is density times gravity times volume, the density here we're talking about is the density of cold air, because that's the fluid that's been displaced away. So the balloon's called a hot air balloon, right? There's hot air in the balloon, but the fluid that would otherwise occupy that space is cold air. And the volume then is a fixed volume. So there's no change in the amount of buoyant force. What changes is the vector mg. That's because the mass comes in two parts, doesn't it? There's the mass of the hot air plus the mass of everything else. The basket, the fabric, the passengers. We'll just call all that capital M. So instead of just mg, we can say it's mass of the hot air plus mass of everything else times g. And so by pulling a lever and using a flame to heat up the air, you can change the mass of that hot air, right? Because the hotter the air gets, the less dense it becomes, and therefore the less massive it is. So you really make a hot air balloon rise, not by increasing the buoyant force, but by decreasing the weight, by making the hot air inside less massive. Okay. Similar concept. When it comes to a scuba diver, we can make a free body diagram again, right? Let's see. Let's draw in the weight vector, mg, and we'll draw in the buoyant force. Now, if the two are equal, then we say that the scuba diver is neutrally buoyant. The same thing can be true for a hot air balloon. If the buoyant force and the gravity force are equal, then the hot air balloon is neutrally buoyant. But once one force gets larger or smaller, this is the force in the case of the hot air balloon that's going to get larger or smaller, then it can either be positively or negatively buoyant, meaning it can rise or it can sink. So back to our neutrally buoyant scuba diver. Now, one thing to keep in mind for diving is the wetsuits that are used in diving are a lot thicker than a surfing wetsuit. That's because water has a really high specific heat. When you're surfing, most of your body is above water, and so you're exchanging your body heat with the air, and it doesn't sap as much heat from your body. But when you're totally submerged in the water, and plus you dive at greater depths where the water is colder too, the surface ocean water is a lot warmer than the water at depth. In any case, a dive suit is really thick and it makes you really buoyant. So you just can't dive deep unless you add some weights to make you sink toward the bottom. So a scuba diver wears a BC. That stands for a buoyancy compensator. And a buoyancy compensator has a pocket for some, they're basically just lead weights. And so those lead weights would make you sink to the bottom. Now, this is a problem. At some point, you're going to want to rise back to the surface. So you don't want to have to unbuckle this thing and leave it at the bottom. So to help you either reach neutral buoyancy or rise to the surface, then along with the weight pocket, here's the key to it, there's an air bladder. And that air bladder connects, by a hose to the same oxygen tank that you use to breathe from. And so when you press a button, you allow air to fill up this bladder. And so what does that change? Well, in this case, there's really no effective change in mg, right? Here the mass m is the mass of the person, the wetsuit, their fins, the tank. There's nothing effectively that's going to change. However, when you press the valve and you let more and more air into the air bladder, it expands, and if it expands, its volume becomes greater, and after all, buoyant force is the density of the seawater displaced multiplied by gravity times the volume of seawater displaced, and when the air bladder fills up, it displaces a greater volume of seawater. And so by changing the buoyant force, you can change the balance between the two forces and either establish neutral buoyancy or make the positive or negative buoyancy. Okay, let's put some numbers to all this. What if we had a spherical shell? Some buoys might be in the shape of a spherical shell. And we'll make up some numbers here. Say that the radius to the inner wall is, how about 80 centimeters? And then we'll say the radius to the outer wall is about 110 centimeters, or 1.1 meter. And then we'll say it's made of some metal. I don't want to say exactly what, because I don't know if I have densities of metals off the top of my head, but maybe this is about 7,900 kilograms per cubic meter. Okay, there may be some metal with that density. And then it's sitting in seawater with a density of 1,025 kilograms per cubic meter. Oh, I've gone too far. I apologize. The inner diameter is not 80 centimeters. I misspoke. The inner diameter is unknown. If this is the density of the spherical shell, and this is the density of the seawater, and we know the outer radius, then what would the inner radius have to be so that it floats exactly halfway submerged? Okay, well, start with the free body diagram. This whole buoy has some weight to it, so there's the vector mg, and because it's partially submerged, then it's subject to Archimedes' principle, and it experiences a buoyant force equal to the weight of the fluid displaced. If it's floating halfway submerged and reaches an equilibrium, then we're assuming these two vectors are of equal length, so we state that mathematically. The buoyant force is equal to mg. Great. Well, buoyant force is density times gravity times volume. Density of what? Density of the fluid, and volume of what? The volume of the fluid displaced. Okay, and that has to equal mg. Which m? The mass of the whole buoy times g. But the mass of the whole buoy is equal to the density of the buoy material multiplied by the volume of the buoy material. Okay. Well, we have a g on both sides of the equation, so we can factor that out. So let's take our work up here where we have some room. It says the density of the fluid times the volume of the fluid displaced has to equal the density of the buoy times the volume of the buoy. Easy enough. Let's look at our picture and see if we can figure out what's the volume of fluid displaced. So let's call the radius we're trying to solve for, lowercase r, and let's call the outer radius that's given capital R. So what's the volume displaced? Well, it's all of this shaded region, meaning it's half the volume of a sphere of radius capital R. So this says the density of the fluid, which is given, that's our seawater, 1,025 kilograms per cubic meter, multiplied by half the volume of the sphere. So 1/2 volume of a sphere is 4/3 pi r cubed, and in this case we mean capital R. Okay. On the right side of the equation, density of the buoy's material, which is given 7,900 kilograms per cubic meter, times, let's see, the volume of the buoy. Well, that's just this shaded region. Which we can find by taking the volume, 4/3 pi capital R cubed, and subtract from it the missing volume, the hollow part, which would be 4/3 pi little r cubed. Now there's a 4/3 pi in every term, so let's get rid of that. 4, 4, 4 gone. 3, 3, 3 gone. Pi, pi, pi gone. So now we have the density of the fluid times the large radius cubed is equal to 2 times, there we go, we've multiplied both sides of the equation by 2, is 2 times the density of the buoy material multiplied by big R cubed minus little r cubed. What are we trying to solve for here? We're given both densities, we're given capital R, we want to solve for lowercase r, so it's just a matter of algebra from here. Let's distribute the 2 rho. So we have rho fluid times capital R cubed is equal to 2 rho buoy capital R cubed minus 2 rho buoy little r cubed. So 2 rho buoy little r cubed is equal to capital R cubed times times 2 rho buoy minus rho fluid. So moving over here where we have room, little r cubed is equal to big R cubed times double the density of the buoy material minus the density of the fluid, all divided by 2 times the density of the buoy material. Or we could say it's equal to big R cubed times the quantity 1 minus the density of the fluid divided by 2 times the density of the buoy material. So if we take the cube root of both sides of the equation, we get a final algebraic expression. The inner radius is equal to the outer radius multiplied by the cube root. We can say that as put in brackets and raise it to 1/3 power. That's our way of saying the cube root of 1 minus the fluid density over 2 times the buoy material's density. Let's plug in the values that were given. This would be 110 centimeters multiplied by 1 minus the fluid density is 1,025, and 2 times 7,900, and all this we take as a cube root. Grab your calculators, see what you get. So I get 110 centimeters multiplied by 0.9779, or in other words, 107.6 centimeters. Okay, so this is a rather thin shell, right? If the inner radius is 107.6 and the outer is 110, then that means the thickness. Maybe that's how we should ask this question. What's the thickness of this shell? And it's 110 centimeters minus 107.6 centimeters, which gives us about 2.4 centimeters thick. Here's another problem. You're in the ocean, you see an iceberg, and we'll model the iceberg as a cone. That's generally the idea, right? The portion that's submerged tapers to a point down below. So the question is, if you see a certain height above the water, then how much depth is below water? No other variables are given. Just what's d in terms of some constant times h, or in other words, by what factor is d greater than h? So let's label some more values here. Let's draw a bit of a circle where the cone intersects the surface of the seawater. So let's again label two different values of r. There's a capital R and there's a lowercase r. And then, we can see a right triangle. Actually, there's three right triangles to look at here, right? There's a right triangle and a right triangle. So maybe you see this small right triangle, or maybe you see the larger right triangle, or maybe you see a right triangle that takes into account the difference between the two. Okay, so the full distance, how about we give a name to that, and we call it y, where y is equal to d plus h. So if the iceberg is floating, then we have neutral buoyancy, and our free body diagram suggests that the buoyant force vector matches the gravity vector, Fb, and mg are equal. And by Archimedes' principle, Fb is rho times g times v, which rho, the density of the fluid, and which v, the volume of the fluid displaced. We can replace mg with with rho v times g, and here we mean the density of the iceberg times the volume of the iceberg. So if we set these two equal to each other, density of fluid times volume of fluid times g equals density of iceberg times volume of iceberg times g, then the g cancels out. Now, the volume of the fluid displaced. The volume of the fluid displaced, well, that's this shaded area. That's all of this. But that itself is the shape of a cone, right? It's just a cone with a height of d. What's the formula for the volume of a cone? Isn't it 1/3 pi r cubed? So that's exactly what we have here. 1/3 pi, which r do we mean? Well, if we're talking about the fluid displaced, then the r is lowercase r. So 1/3 pi lowercase r cubed, and that has to equal the density of the ice times the volume of the whole iceberg. Well, the volume of the whole iceberg is a cone, but it's the full cone, so this is 1/3 pi capital R cubed. 1/3 cancels out, the pi cancels out. This is looking pretty easy. It looks like capital R cubed over little r cubed is equal to the density of the fluid divided by the density of the ice. Or, in other words, how about we take the cube root of both sides of the equation. Oh, what have I said? Oh, what a knucklehead. Hopefully you caught my mistake. 1/3 pi r squared h is the volume of a cone. My goodness. So, let's try this again. We have the volume, well, let's start over. Capital R and lowercase r. Buoyant force is equal to gravity force, so rho of the fluid times volume of the fluid times g has to equal density of ice times the volume of the whole iceberg times g, and the g cancels out, and we need to substitute for the volume of the fluid displaced, which is the volume of this cone. Now remember, we've said that this is a depth of d, so this is density of the fluid times 1/3 times pi times little r squared times d. There we go. And that's equal to the density of the ice times the volume of the whole iceberg, which is the whole darn thing. Now it has a height of, what do we call that? Y? Sure. Y, that's equal to h plus d. So this is, let's see, 1/3 pi capital R squared times y. So, like I was saying, the 1/3 and the pi both cancel out, and then we have the density of the fluid divided by the density of the ice is equal to capital R squared y divided by lowercase r squared d. And this is where the right triangle comes in. So the ratio of r divided by d is the same thing as the ratio of capital R divided by y. So if we cross multiply, we get y over d is equal to capital R over lowercase r. So we can replace this y over d right here with a capital R over lowercase r, and we get the density of fluid divided by the density of the ice is equal to capital R cubed over lowercase r cubed. Okay. So now whatever we do to one side of the equation, we do to the other. So we take the cube root of both sides of the equation, and this gives us big R over little r is equal to, how about I write it a different way? Instead of writing cube root, I say I raise to the 1/3 power. So capital R over little r is equal to the cube root of the density of the fluid over the density of the ice. But then again, this ratio of capital R over little r is the same thing as the ratio of y over d, so let me write it that way. Y divided by d is equal to the density of the fluid over the density of the ice to the 1/3 power. And y is the same thing as d plus h, so d plus h over d is the density ratio to the 1/3 power, which means d plus h is this ratio times d when I cross multiply, right? So h is equal to d times the quantity, density ratio to the 1/3 power minus 1. So, finally, we get D is equal to H divided by the cube root of the density ratio minus 1. So what's that tell us? Well, let's take the case where the density of the fluid is equal to the density of the iceberg. Then this whole quantity would be 1, and the cube root of 1 is 1, and 1 minus 1 is 0, and division by 0 gives us infinite, meaning the only way you could have any height of an iceberg, even if it's the slightest amount, stick out above the surface is if the iceberg extends to an infinite depth in the case where the density of the iceberg and the density of the fluid are equal. Of course, that's never the case. The density of the fluid is seawater, which is about 1,025 kilograms per cubic meter. And the density of the iceberg, well, that's the density of ice, and the density of ice is about 920 kilograms per cubic meter. So given those values, you see there's no other variable in the equation, right? If we know the two densities, then we can express the depth of the iceberg as some multiple of the height above water. So let's see what that comes out to. D is equal to H divided by the ratio of 1025 over 920 cube root. Subtract 1 from that. Now let's see what we get. Try it on your calculator and see. So I get D is equal to H divided by 0.03668 approximately, which is another way of saying about 27.3 times H. So what if you were in the ocean and you saw an iceberg, assuming it's in a conical shape, and you notice that 10 feet stick out above the water? That means there's 273 feet below the water.